So today I will again talk about Galilean transformations, and I will talk about invariance of certain physical laws under Galilean transformation. Invariance under Galilean transformation. As we have discussed in the earlier lecture that let me go back, let me check whether I have done that or not. Is it so? I talked about this, and okay, so first of all I will talk about that certain laws which are invariant under Galilean transformation. So first of all, let me talk about that it's a line element, or the length of the line element, or I can say that distance between 2 points is invariant under Lorentz transformation. This LT represents Lorentz transformation in rest of my lecture. So let me draw a Cartesian coordinate system. This is one Cartesian system, and say some object is placed along x-axis, and say this is placed here. It is certain object which is placed here, and say this point is A and another end is at point B, and say when it is seen from this stationary frame of reference, this coordinate is known as x1, and when it is, and the coordinate of the another end will be x2, and say it is it is z-axis, it is x-axis, and if I draw it in this way, then it is in this direction it is x-axis, and say it is y-axis, so it is xyz. Similarly, when there is another frame of reference, say this is another frame of reference, when it is seen from this frame of reference, say it is x prime, it is y prime, and say it is z prime. So when this object is seen from here, then it is basically its coordinate will be x1 for end A, and for end 2 or the end B, its coordinates will be this one, sorry, x1 prime, the x2 prime. So but this frame is stationary, and let us call it as S frame, and this frame is known as stationary frame. On the other hand, this frame is S prime frame, and let us call it as a moving frame, and it is moving with velocity v along this direction. It is moving with velocity v. So in t time it has traveled this distance. So how the coordinates are related in the two frames of references? So as I know that this AB distance is basically in stationary frame of reference is x2 minus x1. What is x2? And in the prime frame, AB distance is equal to x2 prime in the x1 prime. Let us call it as a prime B prime, just for the sake of simplicity. It's like this. And so now let me start with the x2 prime and the x2 prime minus x1 prime. So x2 prime is basically, it is x2 minus vt, because it is moving with the velocity v along x-axis. And similarly, This x1 prime can be written as x1 minus bt. So what it will become, it is x2 minus bt minus x1 plus vt, and this will cancel out with it, and it is x2 minus x1. So in this way I can write down it, it is equal to ab. So that means what will happen, the line element will remain the same, means line element or the length of the line element remains same when it is seen from the either with the stationary frame of reference or the moving frame of reference. So what does it mean? It means that this is basically invariant under Galilean transformation. So it is invariant. So what conclusion we are drawing, that it is invariant under Galilean transformation, right? And go to the next page. Next thing what I want to talk about, the velocity. I want to check that whether the velocity is invariant or non-invariant. Invariant or non-invariant. So I want to check this whether it is invariant or the non-invariant. So as we know that if I recall general expressions, that is say r vector can be written as it is r minus vt. This is it. So for velocity, what I need, say I have to find out the dr prime over dt. Let us take derivative on both sides with respect to time. So it can be written as dr upon dt minus vt. So it can be written as dt over dt. So it will get, so dt upon dt is basically 1, and this quantity comes out to be 1. So I can write down it as a dr prime over dt, and it is dr upon dt towards this side. What should I do? Because for this what I have to do, because it's a r prime, so what I need in this side it's a dr prime by the dt prime. So for that what should I do? Let us put it dt prime here and dt prime here upon dt. So whether I will write down this term or this term, both are mathematically equal, and as we know that t prime is equal to t under the Galilean transformation, so I can say that dt prime is equal to dt. So that means dt prime over dt is nothing but it is equal to 1. So that means this thing will not affect the equality. So but its value will be 1. So that means dr prime by dt prime, it can be written like this, is equal to dr by dt, and this minus v also remains here. So that means u prime is equal to u minus v. So that means the velocity of the object will not remain invariant quantity under Galilean transformation, because for the velocity to be invariant, u prime must be equal to u, but we are not getting this one. And what is this u prime? U prime is the velocity of the particle when it is seen from the moving frame of reference, and u is the velocity of the particle when it is seen from the rest frame of reference. And from this particular expression which I am deriving here, we are concluding that velocity is not a invariant quantity, not a invariant quantity, right? Now let us go to the acceleration, because these all the articles are related to each other. So for acceleration, what should I do? As I know that u prime is equal to u minus v, if I again take derivative of both sides with respect to time, then it can be written as this one, it is dv upon dt. As we know that v is the velocity of moving frame, and it is a uniform velocity. So uniform velocity means this the v vector is a constant. Let me put vectors here over this here because I missed it earlier also. You just put it like this and this one, but the v is a constant. So what does it mean? That means its derivative with respect to time, because it is not changing, so that's why it is 0. So this quantity will be 0. So I can say that du prime over dt is equal to du upon dt, but this can also be written like this: du upon dt, as I discussed above, it is dt prime over dt, and this is nothing but this is 1, it is du over dt. So it can be written as like this. So therefore I can write down that this is du prime over, sorry, prime is here, du prime over dt prime is equal to du prime over dt, which implies it is the acceleration of the particle in the stationary frame, moving frame of reference is equal to acceleration of the particle in the rest frame of reference, and both are equal. So that means acceleration in both the frame of reference comes out to be constant. So we can say that acceleration is a basically invariant under Galilean transformation. And let us do one more thing now. So that's again very interesting. Let us now switch to the Newton's laws. As we know that second law of motion, Newton's second law of motion, is the real law of motion. So if it is real law of motion, what does that mean? That means first and third laws, as you have studied in the lower classes, that can be derived from second law. So that means it's sufficient to check the invariance of this Newton's second law of motion. If this law will become invariant, in that way I can say that Newton's laws are the invariant under Galilean transformation. As I know that as I discussed here above, that acceleration is a invariant quantity. I have to start from there. Also mass is also an invariant quantity, means m prime is equal to m. So that means m prime a vector is equal to m a vector. And what is it? Means the force. And what is Newton's second law? Newton's second law says that the force is equal to mass into acceleration. So what does it mean? That it means that the force in the moving frame of reference is equal to force applied on that body, or the force in the body in the rest frame of reference, and both the forces are supposed to be equal, comes out to be equal. So that means Newton's laws are invariant under Lorentz, not Lorentz, but it's the Galilean transformations. Let me go back under Galilean transformations. Right, so I think today I have discussed that the length element will remain invariant under Galilean transformation, but the velocity is not invariant under Galilean transformation. And but on the other hand, when I talk about acceleration, then acceleration is a invariant under Galilean transformation, and which leads to the invariance of the Newton's laws under Galilean transformation. So I think that's all for today's lecture. In the next lecture I will talk about invariance of the momentum and the invariance of the energy conservation laws, right? So that's all for this.